Hello, my name is Habin Kim, and today I will present the paper Text2NeRF. This paper proposes a method for generating a 3D scene using only a text prompt. One major challenge in text-driven 3D scene generation is the lack of paired datasets. Unlike text-image datasets, paired datasets of text and 3D scenes are very limited. To overcome this problem, previous works tried to generate 3D scene using pre-trained text-to-image generative models, such as image diffusion models. However, these methods often produced results with simple geometry and unrealistic appearances. The authors argue that this limitation comes from relying mainly on deep semantic priors from text-to-image models, because it is hard to capture sufficient low-level geometric and texture details from these priors. Therefore, the authors propose utilizing images generated by diffusion models to construct 3D scenes. Before introducing Text2NeRF in detail, I'll first briefly explain NeRF. NeRF is a 3D scene representation proposed for novel view synthesis. Given only sparse input views, meaning a set of 2D images and camera poses, NeRF can render the scene from arbitrary viewpoints. NeRF can be interpreted as a continuous volumetric function that takes a spatial location and a viewing direction as input, and outputs volumetric density and view-dependent radiance at that location. This function is implemented using an MLP, represented as f sub theta in this figure. The rendering process in NeRF works as follows. First, for each pixel in the image, a ray is generated from the camera center through the pixel using the camera pose. This ray passes through the 3D scene, and multiple points are sampled along the ray. For each sample point, the MLP predicts its color and density. Finally, the colors and densities are accumulated using volumetric rendering to obtain the final pixel color. Since this entire process is differentiable, the model can be optimized using only images and camera poses. The NeRF rendering process can be expressed mathematically. For a camera ray, the expected color along the ray between the near bound T sub n and far bound T sub f is defined as equation 1. Here, large T represents the transmittance along the ray. Since the volume density sigma represents the probability that the ray terminates at location x, the transmittance can be interpreted as the probability that the ray travels through space without colliding with any particles. Therefore, equation 1 can be understood as accumulating colors along the ray until the ray terminates. One important point is that the ray direction D is also used as an input when predicting the color C. As shown in the example figure, even at the same 3D location, the observed color vary depending on the viewing direction. For this reason, NeRF predicts view-dependent color, or radiance, rather than using a single fixed color for each point. Now, let's return to Text2NeRF. The proposed method begins with an image generated from an input text prompt using a pre-trained image diffusion model. This generated image serve as the content prior for constructing the 3D scene. Next, depth estimation is performed on the generated image to extract geometric information. The resulting depth map is used as the geometry prior of the scene. Using the generated image and depth map, the authors initialize a 3D scene through a method called Depth Image Based Rendering, or DIBR. Starting from this initialized scene, the method progressively expands the scene by incorporating information from additional viewpoints while optimizing the NeRF. Whenever a new view is added, image inpainting and two-stage depth alignment are applied to maintain consistency with both the original text prompt and the previously optimized 3D scene. This overall process is referred to as progressive inpainting and updating, or PIU. By repeatedly applying PIU, the NeRF parameters are updated through gradient descent using loss functions designed to improve both pixel-wise rendering accuracy and the geometric consistency of the generated 3D scene. Now I'll explain the scene initialization process in more detail. First, a pre-trained diffusion model generates an initial image I sub 0 from the text prompt P. Then a pre-trained monocular depth estimator F sub E predicts the depth map D sub 0 of the image. However, initializing a 3D scene from only a single image can easily lead to overfitting and geometric ambiguity. To address this problem, the authors construct a support set at sub 0 using a method called DIBR. DIBR estimates how the initial image I sub 0 would appear from another camera pose P sub I by performing depth-based warping. Given the camera intrinsic matrix K and camera poses P sub 0 and P sub I, the warped pixel coordinates and depth values are defined by equation 3. In the paper, 8 additional nearby views are sampled around the initial camera pose P sub 0 along a small circular trajectory. As a result, the scene is initialized and the NeRF is trained using a total of 9 views from P sub 0 to P sub 8. In the original NeRF formulation, view-dependent color is modeled to reproduce effects such as specular reflections. However, Text2NeRF does not use the ray direction when predicting the color of sampled points. This design choice helps the model focus more on maintaining consistent 3D geometry across different views. When progressively incorporating information from new viewpoints, it is important to preserve consistency with previously learned views. To achieve this, the following process is applied when rendering an image from a new camera pose P sub K. First, previously learned views are warped into the new viewpoint using DIBR. Regions that cannot be represented through warp are masked. Then a pre-trained diffusion model performs inpainting using the warp image, the mask, and the original input text prompt. The resulting inpainted image is denoted as I hat sub k. Using the NeRF optimized up to k-1's view, the rendered depth map at viewpoint p sub k, denoted as d sub k superscript r, can be computed using equation 2. However, the estimated depth map d sub k superscript e, obtained independently from the inpainted image, may not align well with the already accumulated NeRF geometry. Therefore, the authors apply a two-stage depth alignment process to align d sub k superscript e with d sub k superscript r. The first stage is global alignment. In this step, random pixel pairs are sampled from overlapping regions of the two depth maps, and the average scale and offset differences are used to globally correct d sub k superscript e. The corrected depth map after this stage is denoted as d sub k superscript global. The second stage is local alignment. To further correct local nonlinear inconsistencies, a learnable pixel-to-pixel network, f sub p, is applied. The final aligned depth map is denoted as d hat sub k. As discussed earlier, the inpainted image I hat sub k and aligned depth map d hat sub k are used to further optimize the NeRF. To maintain consistency across viewpoints, the authors propose a progressive inpainting and updating strategy, or PIU. In this strategy, the NeRF is updated sequentially after each inpainting step. As a result, once a region has been inpainted, the generated content becomes part of the scene representation and is reflected in future renderings, preventing the same region from being repeatedly inpainting in later views. Finally, let's look at the loss functions used for NeRF optimization. The first is the RGB loss, which is an L2 loss between the color values of the NeRF rendered image and those of the image generated or inpainted by the diffusion model. The second is the depth loss, defined as the L2 loss between the rendered depth map and the aligned estimated depth map. The final component is the transmittance loss, which encourages the NeRF to minimize density values before the ray reaches the expected depth location. These three losses are jointly used to optimize the NeRF. The authors compare their method with 7 baseline models. Since scene generation does not have GT reference images, the paper evaluates images quality using no reference image quality assessment metrics, specifically BRISQUE and NIQE. In addition, the paper reports the CLIP score. This score measures the similarity between the embedding of the generated image obtained from the clip image encoder, and the embedding of the text prompt obtained from the clip text encoder. Therefore, the clip score evaluates how well the generated scene semantically matches the input text prompt. This figure shows a comparison between Text2NeRF and the baseline models. The proposed method achieves lower BRISQ-UE and NIQE values, as well as a higher clip score compared to the baseline methods. This result indicates that Text2NeRF generates visually high-quality 3D scenes, while also producing scenes that better reflect the input text prompt. The authors also conduct evaluation studies to analyze the effectiveness of the proposed components. In this presentation, I'll briefly focus on the results related to PIU, depth loss, and depth alignment. First, regarding PIU, when independent inpainting is performed for each view without applying PIU, view inconsistent inpainting results are incorporated into the NeRF. As a result, shiver artifacts appears in overlapping regions between different views. Both the qualitative and quantitative results demonstrate the importance of the PIU strategy for maintaining multi-view consistency. Next, let's examine the results related to the depth loss. The authors compared their proposed L2 depth loss with two existing depth losses, GNLL and SSI. The experiments show that using any type of depth loss produces better results than not using depth supervision at all. However, the proposed L2-based depth loss generates the most plausible geometry and helps synthesize the more realistic novel views. Finally, let's examine the result related to depth alignment. In Figure A, depth alignment is not applied at all, resulting in abrupt depth changes caused by inconsistencies across viewpoints. In Figure B, only global depth alignment is applied. Although the overall depth structure becomes more aligned, fine local details are still not sufficiently corrected. In Figure C, only local depth alignment is applied. Some inconsistencies are reduced, but the problem is not completely resolved. Finally, Figure D shows the full two-stage depth alignment strategy. Compared to the previous cases, smoother and more consistent depth transitions are observed. In conclusion, this paper proposes Text2NeRF, a framework capable of generating realistic 3D scenes with complex geometry and high-fidelity textures using only text prompts. The method utilized a content prior generated by a pre-trained diffusion model and a geometry prior estimated by a pre-trained depth estimation model. To represent the 3D scene, the authors employ NeRF and progressively optimize it through the progressive inpainting and updating strategy. During this process, view consistency is maintained through text-guided inpainting, while geometric consistency is improved using two-stage depth alignment. In addition, the objective function incorporates depth and density-related losses for depth-aware NeRF optimization. As a result, Text2NeRF is able to generate diverse and geometrically consistent 3D scenes from natural language descriptions. However, the method still has several limitations. The authors point out that Text2NeRF struggles in scenes with severe occlusions, mainly due to the limited accuracy of monocular depth estimator. Inaccurate depth prediction causes geometric distortions during the IBR-based warping, and these distortions become more severe as the camera movement increases. As a result, unrealistic artifacts may appear during the painting stage, making it difficult to generate plausible scenes. The authors suggest that future improvements in depth estimation could help addressing these limitations. Thank you for watching.